Sometimes the best answer is the most obvious one. And sometimes, if you venture far enough beyond the obvious, you eventually find yourself right back where you started. What is life? And what does it mean to be alive? Well, you could spend a lifetime tinkering with these impossible riddles. You could twist their words inside out and upside down until the letters melt into the abstract. You can dig endlessly into the void, staring at time scales which are far too big to mean anything, and where everything that exists is revealed to be ephemeral as the drops of rain falling from the clouds. But go even further, and eventually, something unexpected happens. You emerge from the void, disoriented and still helplessly puzzled, but you take a look around and quietly realize that your path forward has become a loop, and the answers you were seeking were already in front of you. You find yourself exactly where you started, and nothing has changed, but you changed on your journey. Many of our deepest existential questions seem to lead us in circles, yet those circles may be precisely where the meaning lies. Philosophy isn't the only place where you can find these mystical loops of reasoning. In fact, the field of mathematics is no stranger to them either. And certain mathematical problems are endowed with an unexpected structure, invisible at first glance, that allows them to essentially resolve themselves using a technique called recursion. And to see recursion in action, let's take a look at a counting problem. A counting problem in mathematics is a question of how many. So here's the problem. In how many ways can you tile a rectangle which has a width of 2 units and an arbitrary integer valued length of n units? So n could be 1, 2, 3, and so on. By exclusively using either red vertical 1x2 tiles or blue horizontal 2x1 tiles. We'll refer to the length of such a rectangle simply as its size, and we'll let an denote the number of ways in which you could tile a rectangle of size n in this way. So let's start by investigating the simplest possible instances of our problem so we could build our intuitive understanding of how it really works before we attempt to solve it in general. So if n equals 1 and our rectangle has size 1, well, there's only one way in which we could tile this rectangle, by using a single red tile. So a1 equals 1. If n equals 2 and our rectangle has size 2, then there's 2 ways in which we could tile it, either by using 2 red tiles or 2 blue tiles. a2 equals 2. If n equals 3 and our rectangle has size 3, then there's 3 ways in which we could tile it. Red, 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 blue, blue, or blue, blue, red. a3 equals 3. If n equals 4 and our rectangle has size 4, then there's 5 ways in which we could tile it, and those possibilities are shown here. a4 equals 5. But what if our rectangle had a much larger size? For example, what if n equals 100 and our rectangle has size 100? What then would be the value of a100? Well, it would take a lifetime to list out all of these possible tilings one by one. So we need to come up with a better strategy for how we could count these auditors. Also, why stop at 100? What about the general case of this problem, where the value of n can get larger than, say, the number of atoms in the universe? Could we still find the answer then? And here lies the true difficulty of this problem. Not in answering the question for a specific value of n, but rather in devising some kind of pattern or rule or formula which can allow us to calculate the value of any an and concisely capture the essence of what's really going on with these structures. Discovering such a formula would give us insight that could go beyond any rectangle that you could ever write down or even generate on a computer because of the limitless nature of numbers. So what is the answer? What is the pattern? Well, let's imagine that we had one of these random tilings of a large rectangle, say of size 100. We might not know anything about what a random tiling precisely looks like, but we do know one thing. One simple, almost trivial piece of information that might even seem pointless to consider at first glance. We know how such a tiling needs to end. And if we simply ignore the chaos of the pattern that's formed by the first bunch of tiles, a shred of order emerges from the tail end of our shape. Because no matter how our rectangle is tiled, it only has two possibilities for how its tiling needs to end. Either it ends in a single red tile, or it ends in two blue tiles. But how exactly is this observation useful in the context of our problem? Well, in the case where a rectangle ends in a single red tile, what would happen if we removed that tile? What we'd be left with is actually something we've seen before. It's just another one of these rectangles tiled with the same red and blue tiles in some way, but whose size is now 99, reduced by 1, which was the length of that single red tile that we removed. The number of these tilings is A99, and we might not have a specific numerical value for A99 just yet, but we do have a variable for it, and in mathematics, turns out to be all you need most of the time, as we'll see. In the case where a rectangle ends in two blue tiles, remove those, and again, we'd be left with something that we've seen before. Yet another one of these rectangles, tiled with the same red and blue tiles, but whose size is now 98, reduced by 2, which was the length of those two blue tiles that we removed. The number of these tilings is A98. So overall, we could say that any random tiling of a rectangle of size 100 is either a single red tile preceded by some random tiling of a rectangle of size 99, or it's two blue tiles preceded by some random tiling of a rectangle of size 98. And therefore, the value of A100 is equal to the value of A99 plus the value of A98. But there wasn't anything particularly special about the number 100 in this argument. And in fact, we could apply the same logic to a starting rectangle of any size. And in general, we can conclude that the value of an for any n, not just 100, is equal to the previous value, an minus 1, plus the previous value, an minus 2. In other words, the number of tilings of a rectangle of any size is equal to the sum of the number of tilings of the two directly smaller rectangles. And these two values come from the two possible ways in which a tiling of the original rectangle could end. So now we could use this equation over and over again to compute the value of any an. Just keep adding the two previous values in a branching fashion until you get all the way down to the smallest cases that we started with, when we established that a1 equals 1 and a2 equals 2. But there's also a much faster way of doing this computation. If we use techniques in algebra, which I will skip over the details, we could translate this equation, taking into account its initial values, into what's called an explicit formula for an. And here's the explicit formula for an for this problem. And again, I'll skip over the details here, but the key takeaway is that all we really needed to do to obtain this formula and essentially solve our problem was to examine how the objects we were studying could relate to simpler versions of themselves. The answer was already there, staring at us through its lifeless grid lines. And that's all you need to do recursion. You need a starting point, a set of base cases which crystallize the simplest instances of the problem, and then you need a recursive call, an appeal to simpler versions of the same exact problem. Recursion shows us how remarkable problem-solving power can emerge from a rule which simply refers back to itself. If you've heard mathematical talks like this before, you might even recognize the equation we derive, because it's the same recurrence relation that defines the Fibonacci sequence, a famous pattern of numbers that has profound connections to life and to the universe. But counting problems are just one of the many areas, mathematics, computer science, and beyond, where recursion proves to be a powerful tool. In game theory, for example, The optimal strategy to a complex game can sometimes be devised by analyzing progressively simpler game states until arriving at instances of the game where the best move would be obvious, the so-called base spaces. In geometry, ethereal structures like the Mandelbrot set are, at first glance, impossible to reason with, until you zoom in far enough and discover, remarkably, a copy of itself lurking within itself, setting off a mirror-on-mirror effect which has neither beginning nor end. It's a familiar idea because similar self-referential structures exist within complex life forms like ourselves. In fact, DNA is just copies of itself, and zoom in far enough into yourself and you'll find more life forms, cells, bacteria, independently living things. Life exists within life. So what is life, and what does it mean to be alive? Well, in a recursive way, I think you all already know the answer, even if it's not something that you often think about or can easily articulate, because simple ideas can lead to intractable complexity. But life is the feeling that you've always known it to be. It is the breath you take to supply yourself with energy. It is telling your family and friends that you love them, knowing that tomorrow is never guaranteed. It is the moment, the only thing that it will ever be. So the next time you find yourself staring down the barrel of a difficult problem, I invite you to challenge yourself to try and find a solution that might be already staring right back at you. Thank you.